And again, thank you for having me here. Um, I hope and I know that some of you already were presenting in my talk on Monday. Unfortunately, today I cannot be presently with you because I got a bit sick, so I think it's more safe for everybody if I'm talking from campus here. But I'm very close and I'm really happy to discuss all the things that we've been discussing all these days. So I will continue talking about machine learning in reflectometry, but more on the technical side and more with the software related problems. And if you were presented on Monday, you remember that I presented two approaches to reflectometry that we will be developing at University of Tübingen with many collaborators from Graz and Kiel and together with Daphne and machine learning cluster in Tübingen. So the two approaches are, you can think of about this as the replacements of the conventional algorithms. The first one is the replacement of the differential evolution algorithm, and this is called reflectorch, and this is going to be the focus of today's talk. And the other one is PAMPE, the fast and reliable replacement for Bayesian inference methods such as Markov chain Monte Carlo. And I think here it is important to say what is the difference between the talks by the previous speakers and this one. And the main difference is that we are not developing new packages, but rather we're developing new algorithms. Of course, we have the software which I will present, but the main difference is that we don't want to make another reflectivity package because we see how many great packages already developed there, but rather we'd like to make some algorithms which can be shared and used by all the different packages with the different use cases, same way as differential evolutions, for instance, is used by all of these packages. And yeah, just to give some more context, especially for people who presented on Monday, the package of Vectorch I'm going to talk about today is the package that exactly was used in our closed loops experiments a year ago, published in paper. And this is the package which we use to precisely grow the films during the closed loop automatic experiments with predetermined thickness in different settings. Okay, so I will just go directly to GitHub where you can, I hope you can see my screen still, right? This package is shared now on GitHub. You can download it, and many thanks to PhD student Valentin Munteanu from University of Tübingen, who put a lot of effort to make it more accessible for people so that you can already check it and try it out. Of course, it is a bit experimental because, of course, it's all the new algorithms. And I recommend you to install it from source. There is a great documentation here already. And of course, the initial idea of this package was to develop the code which is very flexible and fast for training new models for experiments. This is something which we did a year ago at the ESRF. And there is something which you can do for yourself, actually. So there is a page on documentation where you can look at and check how to train your own models. And it's actually quite simple. You basically have several methods you have to use. It's all, of course, requires some knowledge in Python, but I think we all use Python based on the previous talks, or maybe most of us. And there are some simple configuration files that one can use to provide their own use cases, constraints, parameter ranges, and so on and so forth. But I'm pretty sure that most of you are more interested in another part, which Valentin made accessible, is using already a trained model so that you can use it just from your laptop. You don't need any GPUs, you don't need any CUDA installed. You can just download a trained model and use it for your case. And this is one key difference between machine learning and standard conventional algorithms. And this is a technical challenge because, of course, you need the model for that. And the general wisdom is that you don't want to train one model which covers all the cases and such a big model that you cannot even then run it on your, you just don't have memory to run it on your computer. So instead, you'd rather want to train several smaller models which are used for some use cases. And this is what we are trying to do, and this is what we're aiming to do. And this is the repository on Hugging Face. And for those of you who don't know, Hugging Face is the first, maybe the leading. It's basically GitHub for machine learning models, so to say. So it's the place where you can freely put your machine learning models and then load very in a user-friendly style from your code and use directly. And currently we have here, I think, 70 models which are already trained for different use cases. And these models you can just use from the package. And of course, also it doesn't cover all the reflectometry, and especially the Newton part, we have to work on that a bit. And this is why I actually encourage you to approach me or Valentino or others and share your own use cases and your own models and what you would like to do, so that we can train the model for you, so that you don't have even to think about how to do that. We put it on Hugging Face, and then you can use it straight away. And here's a quick demonstration about how we can use it. So the main method here is just inference model. So you provide the configuration name and the repository on Hugging Face, and it doesn't have to be this one, so we can make some more general repository for reflectivity. And the idea is that, again, we want to collect all the important use cases for you. And once you have that, this is the model which you can run on CUDA, but it doesn't have to be. You can just specify here CPU and run it on very simple laptop. So there are very limited hardware limitations. So it's very easy to run. And you see there is some information here which summarizes the model which you just downloaded with different parameter ranges and other settings that are important for like how the model was trained. And once it's done, you need two things. You need experimental data and you need parameter bounds for your particular curve. So the model, I explained it on Monday, but maybe just repeat it now, that the model is trained on a large range of parameters, but it takes into account your physical knowledge, prior knowledge for every particular curve. So you can specify the parameters, the parameter ranges, and the model prediction will be within those parameter ranges. And it is blazingly fast. So I'm now working like with my laptop, which I think it's CUDA, but it's a very simple CUDA, and it's done basically instantly. So you can see this now I run the prediction and it's super fast. Now, this is all good, but one thing I'd like to put attention to is something which conventional analysis is not really interested about, but it's very important in machine learning. And this is something we call unit invariance in reflectometry. And the idea is that if you think about the parameters of that come in as an input to your reflectometer simulator or the reflectometer engine, Q values, thicknesses, roughnesses, SLDs, you can scale them. You can rescale them to achieve the same curve, but for different Q values. So the idea is that your Q values are, let's say, in inverse angstroms, thicknesses are in angstroms, sharpnesses in angstroms, SLDs are inverse squared angstroms multiplied by 10 to minus 6, it doesn't matter. So you can now use some scaling coefficient to change these units, let's say 2. And as a result, you get Q range, which is changed by the curve stays the same. And here it is demonstrated a bit better. So you can effectively squeeze the Q range. And this allows you to use the same model, which is trained on one Q range, but for very different Q ranges during inference. And this gives you great flexibility, but at the same time is a challenge because you have to kind of figure out which parameters can you use, which models can you use, because there is this flexibility resulting from scaling invariance. So to summarize, this is the package that you can already use. I would be really happy to if you can give us some feedback. It's a bit experimental, of course. It's been put on GitHub just a week ago, maybe less than a week ago. And yeah, thank you very much.